So, yeah, because we're in a new notebook, we need to set things up again. So we just import the same things. And the really important thing here is that we use the same event label as we did in previous steps. You'll notice that there's this error warning about not being able to import Catwoman. This is because of Python reasons and weird AWS reasons. So if you're running this locally, you shouldn't see this error message. But yeah, regardless, we won't be using this Catwoman tool, and we can continue ahead. And again, you want to set up the exact same path. This is how we're going to connect the stage 4 outputs to the inputs of stage 5. Then in here we have kind of an introduction to Bayesian statistics. I'm going to skip over this, and I mostly just copied it here in case you're interested in kind of a more detail behind some of these words that I'm going to be saying. Some important things we're going to be doing is maximizing the likelihood, which is this term here. And we're going to be also including a prior, which is this term over here. So we're going to be maximizing likelihood using prior, computing posteriors. So these are all kind of Bayesian statistics, which is kind of just a fancier version of least squares. But with least squares fitting, you kind of get a best result. And with this Bayesian statistics, we're going to be doing things to get uncertainties on our fitter parameters, which is kind of the most important aspect of all of this. To be doing our fitting, we're going to be using nested sampling, which is a specific sampling technique. I and many people often call this a fitting technique. It is not fitting. It is sampling, and it in a way can be approximated as a fitting technique. But it's basically going to semi-randomly sample all across your prior space and find, what is the likelihood that the data could be produced given your model at that point. And so it'll go through a whole bunch of range of things that you're allowed to explore, and it's going to tell you that parameters around this value are a good fit to the data. We'll be using the dynasty nested sampling algorithm, largely just because it's really fast for this use case, and that it has a really nice stopping condition. A lot of more older style Markov chain Monte Carlos, you have to write your own code to run them, or you need to run them until you know that it's converged, and knowing how something converges is a whole nightmare. And so Dynasty has a pretty nice way of just running until it's converged and stop. So yeah, it's really useful tool. And it can also be really useful for model comparisons using Bayesian evidences. Again, that's a slightly more complicated topic, and there's some more discussion up here of how you might do that. So getting to this ECF, I'm actually going to switch back to this output light curve here to kind of talk about how we're going to fit this thing. So generally, when you're fitting a light curve, there's a couple of decisions you want to make. One is, what is your astrophysical model? Are you looking at a transit observation? Are you looking at an eclipse observation, a phase curve observation, things like that? So here we have an eclipse, so we're going to want to use some kind of astrophysical model to fit this. For our purposes, we're going to use the Batman model from Laura Kleiberg et al. And so that's a very simplistic eclipse model. And as we'll see later, we'll see if that assumption is good enough. But it just assumes that the planet is uniformly one brightness. And so, that describes its ingress, baseline, and then the egress. Looking at our observations, which you should absolutely always do before you fit them, you should look at them, scratch your head, and think, what do I need to fit this? So you see that there's this strong curve at the start of the observations. So that, there's different ways of handling that. You can fit exponentials because it looks like an exponential decay. And there's kind of physical reasons why we might expect an exponential decay. Another option available to you is kind of cutting out a bunch of the initial observations. That way you don't have to fit something so strongly curved. And so the general recommendation is for transits and eclipses that you have half an hour of detector settling at the start of your observations to get rid of the worst of this curvature. And then you can just throw away those data and not have to fit them. If you want, you can try and fit them. But from experience, it can be really hard to fit them very well. And so it's good to add that extra padding. For phase curves observations, meanwhile, this curvature really takes quite a long time to decay. And from these early release science observations, we found that this curvature can actually be quite correlated with the curvature of your phase variations. And so the recommendation for MIRI observations is that you add about an hour at the start of your observation, so you can cut out basically up to here and really get rid of the worst of that curvature. For our purposes of this notebook, we're going to cut over here, in part to get rid of that curvature, and in part because, as we'll eventually see, this planet is not uniformly bright across its whole day side, and if we don't do that, we get into some nastiness. So, to the kind of Eureka way of the Eureka way of writing this is this run my funcs. Oh, sorry. This run my funcs part of the Eureka template. And so this specifies what functions you're wanting to fit. So as I said, we'll be using the Batman Eclipse function, and we're going to be using an exponential ramp to model the kind of tailing off of this exponential ramp. Even though we're cut off over here, there's still probably a little bit of curvature that's worth handling. You always have to fit a polynomial because you have to fit at least a constant number for the baseline value. And we're also going to fit for a linear slope in time. And then, as Ian mentioned, we fit for the position and the width of the trace on the detector. And we're going to choose to linearly decorrelate against that. So we're going to assume that because the trace moves such a tiny, tiny amount, that any changes in the flux can be assumed to be linearly correlated with the changes in position. So if the position changes by a whole pixel, the flux would change by some amount, and if it changed by half a pixel, the flux would change by half that amount. And as Ian showed, we're dealing with like 1/100th of a pixel change, so that's okay enough estimate. Yeah, the amount of kind of parallel processing you want to do, this number just speeds things up depending on your setup. I think you all within the JWebbinar tool have, I think, 4 CPU threads, so you could set that to 4. And then this parameter here, manual clip, controls how many of those initial integrations we're going to cut out. And I said, for our purposes, we're going to cut this an enormous number of integrations. This is definitely not what the norm is going to be, but we're doing this special case of using an eclipse observation from a phase curve. And so for our purposes, we're just going to cut this part out. And then, as I mentioned, the dynasty nested sampling has this kind of stopping criterion. And so that's what this last parameter here is. It's going to say once our estimate of the posterior volume is converged, then you can stop. And all of these rest of the parameters, they're generally good enough for your intents and purposes. But you can read the dynasty link here if you want to learn more about how to use dynamic nested sampling. And that's largely it for these datasets. It's pretty simple, but that's because a lot of this work is being done by Eureka of all of these models and stuff. That's one nice aspect of Eureka, is that there's all of these hard-coded models. But Eureka is open source. You are encouraged to write your own modules, and if you want, submit them to the repository as well. I would say, and yes, the one last thing that I do kind of recommend doing is that you set this parameter here. This will use the cached outputs of the stage 4 notebook. If you want to use your own outputs, then you can get rid of this and just erase it. That will use the most recently run stage 4 output. But just for reproducibility, or make sure you don't have any weird things. Like if you didn't run this to completion or something like that, you might have weird outputs. And so, we provided you this cached stage 4 output. So we'll run that. And then we get into setting more nuances about these what are there, 5 models. So there's kind of a description of what each of the columns are and a description of all of the parameters that we're going to be dealing with. So we now in stage 5, we have an additional text file called a Eureka parameter file. So this specifies the priors that we want to put on all of our fitted parameters. So the first one we have here is the planet radius. We have the FP, which is the eclipse step. We have some parameters controlling the orbit of the planet around the star. We have a bunch of systematic parameters that control aspects that are more related to the detector than the planet. We have a final parameter here of interest, which is the multiplier. So in stage 4, if you look, you see there's these little error bars on each data point. These error bars are computed assuming that the dn per second that Ian mentioned, that all we have is Poissonian photon limited uncertainties on each data point. In practicality, we have background noise, as we can see, and we have other components to the light curve that can cause not purely photon noise. And so in practice, it's really important that you have this additional noise multiplier term. Otherwise, your transit or your eclipse steps will end up being overly certain. And so that's kind of an introduction to all these parameters. And finally, there's this last one, because we're fitting eclipse observations and we're passing in the time of transit here. We need to account for the fact that light travels at a finite speed, and going from transit to eclipse, the planet has moved further away from us, and so it takes some finite amount of time for the light from that planet to travel to us. So that's what this last parameter is. It's the stellar radius to convert from this semi-major axis in units of semi-major axis divided by stellar radius into some kind of physical units. So the first column is the name of the parameter. The second column is the initial guess of the parameter. It really doesn't matter for the parameters that you're fitting. It really doesn't matter what you're doing as long as it's within your prior. It's just kind of a guess. Your third column is whether or not the parameter should be free or fixed. So freely fitted parameters are ones that you want the code to fit, and fixed parameters are your ones saying, just use this parameter. So for a single eclipse observation, we really don't have much information at all about the radius of the planet compared to the radius of the star. And so we're just going to use this previously published radius from the planet. And similarly, the orbital period and the orbital inclination and semi-major axis are really not well constrained by a single eclipse observation, so we're going to fix those. But we can tell when the eclipse happens, and so we're going to use this transit time as kind of a proxy of when the eclipse happens. So we'll fit for the eclipse depth, which is a parameter of interest, and we'll fit for the eclipse time to make sure we're accounting for when the eclipse will happen. And then for all of our systematic parameters, you basically always want to set these as free. They should almost never be fixed. And so, for each wavelength or for each data set, you're going to end up with completely different values for all of these parameters, so they should be freely set. The next column is, the interpretation of the next two columns is controlled by the final column. So this final one specifies your prior type. So you can use a normal or a Gaussian prior, in which case this is your mean and your standard deviation of your Gaussian. Alternatively, you can have uniform priors, where this is the lower limit and the upper limit of your priors. And so, yeah, depending on your needs, you might want uniform, log uniform, or normal priors. So some parameters like the eclipse depth, we don't want to tell the kit what the eclipse depth is. That's what we want to measure. So we'll use a really huge Gaussian prior saying like, by I, this eclipse depth is, hand wavy about 6,000 parts per million. So we'll say it's hand wavy 6,000, but I don't want to tell the fit that. I want the fit to tell me what the eclipse depth is. So I'm going to say it's 6,000 plus or minus 5,000. Let the fit tell me what to do. Other parameters like the time of transit, we have archival data that we're going to use to constrain that. And then these systematic ones, it becomes much harder. But the C0 is kind of a constant offset. So that's kind of the level out here. Then we have C1, which is the linear slope in time per day. So that one's harder to estimate. And then R0 is the amplitude of the exponential ramp, and R1 is the time scale of the exponential ramp in inverse days. And then these y pos and y width are changes in flux per unit pixel. And so generally speaking, for myriad data, these are decent estimates, but a lot of these will be kind of, you should set the, for normal ones, you should set the prior width to be huge and let the fit tell you. Yes, and so getting to units, this RP is in units of RP over R star. The FP is in FP over F star. So a lot of these are relative units. The period is in units of days. T0 is in the same units of time as your light curve. So for the JWT pipeline produces light curves in barycentric, modified barycentric Julian date in the TDB, the barycentric dynamical time units, and so we're going to stick with that. And so that's how we arrive at that, and I think that's described in more detail, up here. And then inclination in degrees and semi-major axis. If you're wanting to use the impact parameter instead of the semi-major, instead of the inclination angle, you can do that as well. The Eureka documentation goes into a lot of description of how to do that, and that link is there. And so with that, we can kick it off. And because of installation issues, we get a little warning here. We can ignore that for our purposes, but for your own purposes, it is useful that you probably want to run Eureka from start to finish with one particular version. And with everything, it tells you where it's loading things from and where it's saving it to. And so this is really helpful. If you, up here, if you don't say which particular stage 4 run you want to run, it's going to use the latest. And so if you're confused, like why is it not using things, read this. It'll tell you where it's reading stuff from, and you can fix it that way. And so you can see it clips those initial integrations, and then it shows us a plot of our, half decent guess of what the fit should be. And the initial log probability, which is the combination of likelihood and the prior. And so you can see my initial guess, it has the right shape of an eclipse, but the model definitely doesn't go through the data. And so there's definitely some room for improvement. It will then run the dynamic nested sampling algorithm using however many data live points it thinks it needs to use. It'll run this for a while. Depending on the number of CPUs you're using and the speed of your CPUs, this can take up to minutes, depending on the data set. For this one, it should take no more than about a minute for even a slow CPU. For this particular run, it took 12 seconds. So it's, like I said, super fast and does a great job. At the end, we get this log Z, which is the Bayesian evidence. So if you're wanting to compare different nested sampling outputs, you can compare this. And that's really quite beyond the scope of this presentation, but that gives you an idea. One important thing to check is that your reduced chi-squared should be pretty close to 1. And that's the purpose of this scatter multiplier, is to get your reduced chi-squared of 1. And then you get some plots and some text outputs. So the text output are telling you the results of your fit. So the first thing is the median of the fit. Again, this is not fitting, this is sampling. So this is the median of all your samples, and then the plus and minus 1 sigma standard deviation of your samples. So you have all the parameters of interest, and you have some plots. So you can see now the model does quite a good job of going through the data, which is really reassuring. The first panel is in kind of just, the light curve divided by the median of the light curve, and so the units are not super meaningful. The second one, for eclipse light curves, we'll have it normalized so that the base of the eclipse is at 1.0. So this is purely stellar flux, and then any extra fluxes come from the planet. And going from the top panel to the middle panel, the exponential ramp, the linear ramp and timescale, all of those systematic effects have been removed, and it's just astrophysical signal that's left here. And then finally, you get your residuals. In a perfect world, your residuals would look like just completely white Gaussian noise as a function of time. If you look closely, at least to my eye, I see some squigglies going on over here. We'll circle back to that later. The next plot is a RMS binning plot. A lot of people used to call this Allen variance plots, which is a bit of a misnomer, but it basically shows how the noise level in the light curve changes as a function of temporal binning. And so in a perfect world, this black line, which is the kind of empirical RMS, would perfectly follow this red line. And so that would indicate that there is no residual red noise, no residually temporally correlated noise. As in this case, the black line sometimes, and in Spitzer days, would always pull high. JWT is quite well behaved, and so it falls pretty close. But yeah, often you'll see that it pulls a little bit high. And that's in part because of this, squiggly leftover here. And so that's kind of one diagnostic that you can use to be like, okay, well, this isn't good enough. We need to go back to the drawing board, either fix some of our priors or add some more systematic or astrophysical models to try and explain why this squiggles are left in our data. The next plot is not super interesting. It's kind of just looking at these light curves, and are they Gaussian? They're largely Gaussian, even though when looking in the temporal direction, you can see they're clearly not. And then the final plot you get out, so I guess the second last is called a corner plot. And so it's showing these samples for all of your fitted parameters and how they might be correlated to each other. So since our parameter of interest is the eclipse depth, FP, one kind of useful thing to do is to look up this column and see what FP might be correlated with. And so you can see that FP is correlated with C0, which is intuitive. So C0 basically sets the in-eclipse value, and FP sets the out-of-eclipse value relative to C0. So it makes sense that the two would end up being correlated. And so that's looking pretty good. Another useful thing to do with this plot is make sure that things are not, I ran this really quite fast. We have some time, so I'll come up here. If you want your plot to look more filled in, you can either set your run tolerance to a smaller number, or you can set this number of live points to something larger. So if we look down here, we can see that you used 45 live points. So instead, I'm going to use like 121, just something bigger and a smaller tolerance. I'll go through and run it again. And just because of some Eureka things, it'll just cover the plot. And you can watch live now. This d log z, which is what we set our threshold on, is going to slowly decrease from some large value slowly towards 0. And once it's smaller than this threshold, it'll stop. And this log LZ is our posterior volume. And so this is our Bayesian evidence, which is how you might compare different model fits. And now that that's done, we'll see again, the fits basically haven't changed. Our fit was converged quite well, but when we get to our corner plot, we'll see that things are much more filled in, which can be helpful. And so once you fit more light curves, you can get some intuition as to what these things might mean. That R0 is correlated with C1. That's telling you that your linear slope in time and your exponential ramp are kind of correlated. In other words, your exponential ramp isn't very rampy. It's kind of looking pretty slopey. And that's because we cut out so much of this. We cut all the way to like over here. If we had cut zero integrations, your ramp would be very, very different looking from your linear slope. So that's some things that you can look at. And then the kind of last two parameters of interest here are the position and the width. And so as Ian was saying, even though the position of the trace is moving by like 100th of a pixel, our fit is still preferring to linearly decorrelate against that. So our observations are just slightly correlated based on that position and the width of the trace. And if you had observations with really large movements, then these would be more important. And then, you get this final plot. So that's kind of fitting in a nutshell. Going back to this, you can see that there's this kind of squiggly. Just wanted to give you all a bit of a sneak preview as to why this might be the case. As I mentioned, we're using the Batman light curve fitting tool. And Batman assumes that the day side of the planet is uniform brightness. So the kind of point nearest the star is the same temperature effectively as the edges of the planet from the day side. And so in reality, that is not the case. The point nearest the star is the hottest, and the poles and near the Dundas terminator are colder. And so with the era of JWT, we're able to very precisely measure the ingress and egress of the eclipse and the relative timing and shape and everything to get an idea of the brightness distribution across the planet. And so what we're actually seeing here, amazingly, is non-uniform brightness distribution across the planet. And so to do that, we would have to go back and use something other than the Batman eclipse model. Very, very frustratingly, the best option at present, supported by Eureka, is the starry eclipse model. But unfortunately, the starry eclipse model and the JWT pipeline are mutually incompatible. So hopefully within about the next month or something like that, we'll have tools that will work with the current JWT pipeline. But the starry package is multiple years deprecated right now, and so it's losing support. But just a little fun sneak peek of even with this really simple notebook that you can run end to end without really having to change anything, you're already getting into kind of really groundbreaking science, which is fun stuff. Today we're working live through all of these MIRI LRS notebooks, but I wanted to highlight that we also hosted separately MIRI photometry notebooks. And they're nearly identical for most processing. The stage one processing is the exact same, depending on, regardless of what detector you're using. But when we get into stage three, we start getting into some different techniques here. So with photometry, you now have a point source rather than a dispersed spectrum. And so we end up with similar but slightly different processing. So instead of fitting a Gaussian in one dimension, we fit Gaussians in two dimensions to get the centroid position. And instead of having a one-dimensional aperture and a one-dimensional background region, we just do this in two dimensions. So there's a lot of just really similar things between the two. And then you end up with this time series light curve. And again, you get the kind of centroid positions and the changes in the PSF as a function of time. And then a trend in the background. And again, there's this really strong hook in the background light curve. And so all of these photometry notebooks, by contrast, are using a TRAPPIST-1 observation from Tom Green's GTO program 1177, which has also been published in Green et al. 2020. Oh gosh, what year was that? 2022, 2023? Yeah, it's been a while. I can't remember. So yeah, if you're more interested in the photometry side of things, or if you're interested in the Rocky Worlds DDT, there's these separate photometry notebooks that you can work through as well or in instead.